Um, so particle swarm optimization, this is again a swarm intelligence algorithm, essentially motivated by the behavior, the intelligent, collective intelligent behavior of simple agents, resulting in solving complicated, arbitrarily complicated problems or tasks. So PSO, it's again, I've told you, it's a stochastic optimization technique, Kennedy and Elbert in 95, population-based technique. Again, you have multiple solutions, searching for the best solution at any moment. All right, it's a robust, yeah, optimization technique, finds minimum value for a fitness function. The idea is similar to bird flocks, PSO algorithm. The easiest way to visualize that is uh, is by like looking at the way these bird flocks behave. You must have seen like when flocks of birds fly, they actually form a V-shaped structure. It's primarily because every other bird tries to what you call match the position and velocity of the competing ones, and that's the reason why what you call one of them will be leading and the rest will be sort of forming a V-shaped structure. And so here you can presume that a bird is equivalent to an agent, and food is primarily like they're searching for food, and so essentially food or whatever, right? Basically the solution, and then there is the best solution. Basically the P best is the best solution of a particle that has achieved so far. So probably the fastest bird which is moving ahead would be the what do you call the best solution so far, right? Best solution, and have two aspects of the best solution. One aspect is there is a personal best. When a group of particles are moving or agents are moving, agent itself has its notion of best, so that's called a personal best, right? The best solution a particle has achieved so far, it's called the particle's best, and there'll be a global best. This is basically like, so I told you the bird that moves like the that's leading the flock would be probably the one with the best solution. So that's essentially the idea. So particles form optimization, these are the terms that you need to be worried about. One is we are trying to solve an optimization problem, and you have the notion of a solution. All right, so you have the notion of an agent, notion of a solution, you have the notion of some way to quantify the best, right? Best can be personal best or it can be global best, and based on that, so that's being stated again. The basic concept of PSO lies in accelerating each particle towards. So basically, let's recap our problem. Problem is like we are looking for, you have a search space, all right, and in the search space you start somewhere. That's your initial point, and you are looking for a solution, right? And the initial point, like, and as we typically presume it's a single point, but this is a multi-point search, meaning you have got multiple points competing for the best position at any moment. So you have got a group of solutions, that's the initial point, and from there this group can move in some direction. All right, how do you move? For each of the element, each agent or element or particle in this group, you can actually define the notion of, for every individual you have its best so far. So the best solution in terms of a quantification, say for example a fitness function, the solution that it has found so far, right? The best solution it has found so far, and among the group there will be like the global best, meaning any particle in the group in the neighborhood of that collection, in the collection, the neighborhood of any particle would be like the best one among the group. That is called the G best, or the best individual in the group, right? And PSO uses a number of agents, basically number of particles. I told you it's basically not a single point search, it's a multi-point, and you always look for the best solution, right? Each particle is treated as a point, as a candidate solution. Each particle is essentially representing a candidate solution in an n-dimensional search space, which adjusts its flying behavior primarily, like we'll see how do you formally represent it, according to its own flying experience as well as the flying experience of other particles. So when the birds move, like it's being said that what do you call, the bird tried to match, every other bird tried to match the velocity of its neighborhood, meaning at that point in time it will also consider like the points it's on best, hey, whatever I have achieved so far, and also probably the best. That, so essentially it's trying to follow the leading bird, which is essentially the best, right? The best solution. The leading body is essentially the one with the largest value for the velocity. So that's the reason why it came first, right? The rest of the fellows are actually trying to match, and that's how this particular structure, the V-shaped structure, is actually formed. So there is enough of biological explanation around that, and people in physics also to study this behavior. So what I want to say is basically the PSO search follows this norm. Basically, at any moment, any solution can be considered as a part of this. Any agent can be considered to be representing a solution. And in the set of solutions, at any moment, at any instance in time, you can, any particular, any agent representing a solution can say, I have my own experience of my best so far and the global best, like best among the solutions found so far. So these two have to be like, when I update my position as a solution, I need to make sure that I respect the global best as well as my best so far, right? That's what it is. So let's assume that the position X represents position in the search space X. Let's understand position X in the search space represents a solution, right? What do you do here? With a position, I can have the personal best, I'll have a global best, and I will always look for a new velocity update. My update would be in terms of what you call respecting, in terms of some parameters respecting my global best. I mean, the global best for the community as well as the personal best. Let's understand this equation carefully, then things will be easier for you. So each particle at any moment, so you are in a search space, at each particle is essentially representing a solution, and each particle has to update its solution. So xt plus 1 is essentially like update of the solution, will be at t plus 1 is essentially the next solution will be current solution plus a velocity update. Then velocity update is essentially, this is the most interesting part. You can read this particular part of this table, and what it says is, so it has an old velocity and there is a W factor. It's an inertia weight, primarily how much I respect my old value for the velocity. And then there are parameters called C1 and C2. These are essentially constants. These are called learning factors. One C1 respecting, right, the difference between the personal best and my current position. So my personal best, so this is actually a differential. It's actually a difference between the personal best and my current position, and I multiply that with C1 along with a random number which is between 0 and 1. All right. So basically, I give some weights, and I don't like if it is, I'd say okay, 50 and it's 0.5, it means that 25. That'll be the thing. And same random number will be used to basically like do a weighing over the difference between the global best and myself. So what you essentially do is you update your velocity. That's the first step. So from you want to update your solution. So the first step is you compute your velocity, how much to move, right? How much to move, and that how much to move will be decided based on the difference between your best so far and your current position, weighed by a factor, and definitely there is a randomness, and the difference between the global best and yourself, weighed by a factor, and primarily a randomness there. Basically, you introduce randomness so that you always respect. Say, for example, the factor, the 20, I mean, if a randomness is 0.2, which means that I'll only absorb 20% of the weight, right? That's what it is, right? And I actually like, if I do it randomly. So I do it, what do you call, uniformly. The randomness applied uniformly. So what happens is like at any position, so I have a set of solutions, everybody has to move. What do? They update their how much to move is what is completed first, respecting my current position and the best position globally and the best position for me so far. And then what I do is and once I compute that parameter called velocity, I can actually update my current solution. So essentially my entire group of solutions, primarily that population, moves to the next position, right? That's what it is, by updating each of the individual positions. So this is what the update formula, this is the crux of particle swarm optimization, and this is a classic particle swarm optimization, and people have modified these equations with some additional parameters, some sort of weighing, some sort of what you call, essentially like computing some fractions over some heuristics, etc., etc. There are the variants of it. Even we have done something on particle swarm optimization. Maybe like I've done a paper with a student from Indian Institute of Space Technology, IAST, a while ago, and we have done a publication. We've done a publication also. That's applying a variant of PSO and TSP problem. So that's what it is. So PSO is essentially like, so essentially it's again a multi-point search method where the solution, so your problem is posed as a search problem, and you need to have a mechanism for representing a solution. You have a set of solutions, and how do you update the solutions? You essentially, like, you have the notion of a fitness function. With respect to the fitness function, you should be able to compute the fitness of each of these point, right? Once you compute the fitness of each of these point, you at any moment, you know, like the global best and my personal best. Based on my global best for any solution in that population, based on my global best, based on the global best of the population, and what do you call my personal best, what I do is I update my velocity, and using the velocity update my position. That's what it's done. It's done for every other what do you call, it's done for every other element of the population, and then the population moves to the next position, and it keep on doing. Ultimately, some what do you call, criteria are met. Criteria can be, what do you call, you don't see any movement, or you don't get a better solution, right? That's called a stagnation, or it can be as many iterations as you want. All right, let's see how this can be applied. And pseudocode, it can be what do you call, stated like this: randomly initialize position and velocity of particles. So basically, position is essentially the solution, and velocity is how do you move. All right, position, we need to approximately find the best position, right? Basically, the best solution. Terminating condition, until terminating conditions, you for every particle, what you do is you compute the fitness function, update the personal best and global first for particle, and velocity is updated first and the positions updated first, and then you move on, right? You keep moving until you get a solution, right? Let's see how this kind of an algorithm can be used to solve a data clustering problem. And I have got a paper also in this line. I'll show you the paper. I'll give you the crux of the idea. Crux of the idea is simple. Right, I've got a set of data points. I have a data set. I want to cluster the data points. How do you cluster the data points? So let's assume that there are, and we're looking for a partitioning clustering algorithm. Partitioning clustering algorithm is essentially the data is clustered into, say, k partitions. That's what it is. And you have already seen this particular what do you call, minimization in your k-means algorithm, right? So what you do here is so we are looking for a solution which minimizes this objective function. Your objective function is this. So you have seen a very similar algorithm, the same thing in the case of a k-means algorithm. You have got k clusters, j1 running from 1 to k. So you have fixed your k size, primarily the number of clusters. And so for every element of a cluster Cj, what you minimize is, what is this? Is a Euclidean distance. Muj is the center of the cluster. Center of the cluster Cj. Center of the cluster, the centroid of the cluster of the cluster Cj is μj. So xi, for every point element of Cj, what you do is you find the Euclidean distance between that point and its centroid, right? The center of the cluster to which it is getting aligned to or assigned to. So you find what you call the distance between that and its centroid. All right, and you do it for every cluster, and then you do it for a cluster Cj, and so you do it for every other cluster. You add it up, and you want to minimize. You want to find a clustering solution where the distance of distance of any point to its centroid is minimized. That's essentially the point. That's what is done in a k-means algorithm. K-means algorithm essentially tries to minimize this. You will stop when the points don't move, which means that your for every point you have assigned its closest cluster. So this is basically the Euclidean distance. That's what is used here. All right. So idea, how do you apply PSO in solving a data clustering problem? How do you do a PSO based data clustering, right? Using PSO algorithm, can we minimize the same objective function? Can we squared error minimizer? Can you implement a squared error minimizer where this becomes a fitness function? All right, this becomes a fitness function. I can at any moment, if I have a candidate, what is the candidate solution? Hello. Yes. At any moment, what's the candidate solution? So let's assume that I've got 10,000 points. Right. We've got 10,000 points in our cluster. Looks like somebody has unmuted the mic. Let's check it out unless there's a question. Okay. Hello. Somebody has unmuted the mic. Please make sure that you mute the mic if you don't have a question. I can find out who is the person, but I don't want to. Okay, okay, that's good. So let's move on and let's see what's happening there. All right. So in the case of yeah, you're looking at data clustering problem. So you're looking for, yeah, let's assume that you have got 10,000 points and you're looking for a clustering solution with 50 clusters. So you've got 50 clusters, K is 50, and you want to assign 10,000 points to these 50 clusters. That's a problem. And you want to minimize that. The distance of each of the point in the 10,000 points to its cluster is basically which is captured in terms of the distance from the point, its centroid, right, center of the cluster to which it is assigned to, is the Euclidean distance is minimized for a cluster, and it's done for every other cluster. That's your optimization problem, and you want to minimize such a clustering solution. So what is a potential solution? I can create partitions of the data set. That's a potential solution. One solution can be, I'll say point number 1, point number 2, point number 57, point number 570, point number 5732, etc., is cluster 1. That's right, cluster 1. So the cluster 2 is basically, like, if I actually create a vector. How do you create a vector? You can say, hey, there's a first point. I've got 50 symbols, right? I can create 50 symbols. 50 symbols are 1, 2, 3 up to 50. These are my cluster labels. 1 is one cluster label, 50 is another cluster label. I can create I've got 10,000 points. I've got 10,000 points. Let me repeat, I've got 10,000 points. I can create a 10,000 dimensional vector. 10,000 dimensional vector. I've got a 10,000 dimensional vector. If the first point is belonging to cluster 3, I put 3 there. If the second point is belonging to, right, in my candidate solution, if the second point is belonging to 7th cluster, I put 7 there. If the third point is belonging to cluster number 49, I put 49 there. So which means that my vector can capture, right? This is one I just wanted for you to visualize. So you have got one cluster solution. Like, let's assume that my agent size, primarily like the population size that I'm considering is 3, or my population size is 4 or 5, whatever. Let's assume that the population size is 3. So I create 3 vectors of each of 10,000 dimensional size, which essentially is, the first one is one clustering solution where I have partitioned my data into these 50 clusters somehow, and the second solution is again another clustering solution. It's a clustering solution where all the 10,000 points are assigned to these 50 clusters somehow, and the third is also another solution. For each of these 10,000 dimensional vector, which is essentially a population, is a member of the population. So I've got one first member of the population, one clustering solution. It's a partition of the data. 10,000 points are partitioned into 50 clusters. And the second is again, the 10,000 points are partitioned into 50 clusters somehow, some differently, right? And the third is another 10,000 dimensional vector, which says another partition. So we've got 3 candidate solutions for this problem. And for each of these candidate solutions, I can compute what the objective function. And among the 3 candidate solutions, what do I do now? I can compute the notion of, what you call, for each of the candidate solution, I have notion of fitness, right? And there'll be variability, there'll be variation among the fitness values, right? So I think I have conveyed this. So what I'm trying to look for is probably I don't want to get into a local minima, I want to get into a global minima for this fitness function. That's what essentially the point, right? Aim is to partition the unlabeled data set K disjoint classes by optimizing the criteria function. I don't want to spend time here. So we have got every particle or every agent here in our context is essentially a clustering solution. So xi is one agent. Understand that this is one solution. This is one clustering solution, that 10,000 dimensional vector. C1, C2 up to Ck is one solution. Likewise, I have got x1, x2, and x3. I've got 3, 10,000. C1 is essentially, C1 says, hey, what are the points who are falling into the first cluster, right? First cluster. So point number 3 maybe in first cluster, 27 maybe in first cluster, and likewise that vector will represent. Like C2 also, I know like which are the, so instead of 1 to 50, as I mentioned, you can label them as C1, C2 up to C50 if you want to, all right? Where Ci represent the ith cluster. So every solution, candidate solution, is not a cluster. Every candidate solution is a clustering solution. Basically, every candidate solution that we are considering, every xi is not a cluster. I repeat, every candidate solution is essentially a partition of the data set into say 50 clusters as we, or k clusters as we show here, or 50 cluster. 50 is the number of k's, then there is the value of k that you have chosen. So every candidate solution is one partition. So you've got three such partitions, three ways in which the clustering is done. So for each of these each of the partition of each of the candidate solution, I can compute, right? So how do you update, how do you move to, so I've got three solutions now and I've got the fitness value. How do you get to the next, right? How do you essentially do clustering here? Let's look at this algorithm. You can actually initialize some partition, randomly initialize some k partition. So randomly initialize what you call some particles. So let's assume that we are initializing 3 particles with k random cluster assignments. So iteration count is 1, maximum iteration we can stop potentially for each particle, which means that for each candidate solution, for each partition, what you do is basically you can actually, which is xp or xi, calculate the Euclidean distance and compute this function. This is pretty much straightforward. So for each of the candidate solutions, you can essentially compute what you call the value for this function, right? What is your agenda? Find the personal best for any partition, right? It's a first candidate solution. I am here. If I start, I don't have personal best is myself only, right? If I have gone through 3 iterations so far, I've got, this was my personal best, right? I've got the notion of a personal best, and that was my partition. So I've got a vector and the corresponding for every candidate solution. There is a solution. There is basically that 10,000 dimensional vector and its corresponding value, the best so far, right? And me as an individual, right? And among all the solutions, find the personal best and the global best position for each particle. For each particle, there'll be the global best among the 3, which is the best. That's also there, right? Update the cluster center according to the vector and coordinate. What do you do? What do you do here? That's what is coming over here. Let's look at the original formula. How do you update? So how do you update the velocity? Velocity is essentially what is this is essentially, if you look at this, p best is essentially the personal best, and xt is my current partition. So there is, you get a vector. So this is one vector, my current assignment vector, and this is basically like the best vector, right? So there is a difference between the two. There's a difference between, so these are 10,000 dimensional vectors, which is essentially saying like how do you assign. So from the best, this point was here, and on the best, this point was here, but my current position, this point was here. So what's the difference? Essentially, like this point has to be moved there, right? That's what the difference is. So you get a difference vector, and you can get the similar difference vector with the global best also, right? For the global best also, you find the difference between me and my global best. So then what you do, you multiply them with C1, C2, and then a randomness, and you may have an old vector. Essentially, you start with 0, right? After some iteration, you have some value, and which is multiplied by a w. So you have some velocity. So you get another vector, right? Vector which will be of dimension, my current dimension, which is in my case, the way I represented, I had a 10,000 dimension. You can go for a better representation, right? So my new position would be my old position plus that particular vector, which is essentially respecting the difference between me and my personal best, and respecting the difference between me and the global best. That is how, right, a document clustering can be implemented using PSO algorithm, right? So PSO algorithm, what do you call it? Theoretically, it's very simple. At any moment, you find the velocity, primarily the moment, right? Respecting my personal best and the global best, right? Respecting the difference between me and the personal best and me and the global best. Once you have that velocity computed, you add velocity, you update the position, and keep moving. That's what it is. And at any moment, if you can represent your problem as a search problem with an appropriate representation of your particle, which is in our case, in the case of document clustering, it is nothing but what you call a vector representing a partition, right? You can do that. So conclusions on swarm intelligence: it's a population-based technique. Optimization problem must be written in the form of pathfinding problem with a weighted graph. In ACO, we can solve that. PSO is a robust stochastic search, basically an optimization technique. That's all for swarm intelligence, and these are, you get typically what you call university questions on this context, and yeah, it's not very difficult. You can, I mean, there are people who have attempted, so you can in similar lines, you can actually codify your what you call TSP problem also. Your TSP problem is essentially an ordering. So for every ordering, you get a solution, right? So what you need to do, right? You need to have a mechanism for creating new solutions. You need to find a mechanism to find difference between the best, global best, personal best, and me, right, as an individual. And then you need to have an update formula. If you can design this, you can actually use PSO. We have done that once with a research student. So if you can actually come out with a new way of new PSO algorithm for solving TSP. Likewise, you can attempt any number of problems. The strategy is pretty straightforward. Make sure that you position your problem in the context of PSO and solve it. Particle swarm optimization idea is pretty straightforward, and I want to stop the discussion on swarm intelligence over here.